first thing we're going to do in example 1 is talk about the difference between these two words in a question. Sometimes a question will say verify, and sometimes a question will say prove. Verify means you plug in one value and check if they're the same, and prove is you show that it works for every single value. So proving is way more powerful than verifying. In fact, if you prove first, you would no longer have to verify anything because you could say, well, I've already proved it's true for every single angle that exists. So obviously it would be true for 30 degrees as well. But if you got a verify question, so we're going to do part A and we're going to verify. Verifying is the same as a proof where you draw a line, except on the left-hand side, you replace the theta with 30 degrees and do the same thing on the right-hand side as well. And in this chapter, you're able to use your pie plate. So if you had this on a test, you would say, okay, I can go to my pie plate, I can go to 30 degrees, cos is the x coordinate. I know that cos of 30 degrees is root 3 over 2. And if cos is root 3 over 2, then I know that secant is 2 over root 3. And same thing on the right-hand side, I could change that secant to 2 over root 3. And now I need to do some mathematics to make both sides the same. So one thing I might look at is I say, well, I have brackets outside here. I could distribute this and see what happens. 2 root 3 times 1 would be 2 root 3. And 2 root 3 times this, well, I'm going to just write it out. 2 root 3 times root 3 over 2. And maybe you'll notice that the root 3's would simplify, the 2's would simplify, and you'd just be left with, like this would be 1 over 1, and this is 1 over 1. So multiplying those all out would just be 2 root 3 plus 1. And now we look, and the right-hand side and the left-hand side are identical. So the left side equals the right side, and it is verified. Woohoo! So a verification question is the same as a proof question, just with numbers. You plug in a number, and then you want to show that the left side and the right side are the same, and you have to use some of your algebra and arithmetic skills to do that. How do you work with fractions? How do you work with radicals? How do you multiply and simplify so that both sides are identical? Now, if we were to prove this question, okay, a proof is more powerful than verify. If you prove something, that means it works for all angles. So again, I would probably use our main strategy, and I would change everything. I'd change my secant to cos. I would keep cos the same. And then I would think, well, how do I multiply fractions? Well, this would be over 1. So if I multiplied this, I multiply the tops, I would get 1 plus cos theta over cos theta. And on the right-hand side, if I wanted a single fraction, I'd need a common denominator. So I'd multiply this 1 by cos theta over cos theta. Okay. I want you to, if you're writing down what I write down, I want you to look at your notes right now. And did you write cos theta, or did you decide just to write cos without the theta? This is a very common error. It's an E3 error if you don't write a theta. Okay? If you're doing it in your notes as we go through it right now, you will do it on a quiz and you will do it on a test. Because you're like, oh, It's just shorter if I don't write the theta. Is it good enough if I just write cos and cos? Actually, no, because without writing the angle, COS means nothing mathematically, okay? And so that's a very important letter. That theta is important to be in there. So you get an E3 error if you forget a theta anywhere in a proof. Even off to the side, like in the corner of a proof, if you go tan equals sine over cos and you don't write thetas, I have to take an E3 error off for that. So we just want to make sure that we are always including the angles when we're writing this. Okay, so with that, now I have a common denominator. So my denominator is cos theta, and I add the tops. This will be cos theta plus 1. And my left side and right side are the same. So my proof is done. For part B, we are just going to prove. I'm not going to get you to do, I'm not going to get you to verify for part B. So here's part B. I'm going to prove this in two different ways. First, I'm going to use our main strategy because getting good at this main strategy is so important. But then I'm going to show you that the main strategy is not always the shortest strategy. Or in some of your minds, you might feel like the other strategy we do is a better strategy. So we need to know how to do the main strategy. So this is good practice. The main strategy is change things to sine theta and cos theta and get a single fraction on both sides. So starting this one off, on the left-hand side, I would change tan theta to sine theta over cos theta. On the right-hand side, I would change each of my cotangent thetas to cos theta over sine theta. And you might notice on the right-hand side, I made like my main fraction line darker and thicker and longer, just to remind myself where my fraction was. On the left-hand side, I don't have a single fraction. I'm subtracting, technically this is 1 over 1, I'm subtracting two fractions. How do you subtract fractions? You need a common denominator. So I will take this first one and multiply the top by cos theta and the bottom by cos theta. That would get me a common denominator of cos theta, and my top would be cos theta minus sine theta over cos theta. So I have now a single fraction on the left. On the right-hand side, we have fractions inside of fractions. And on Friday, when we started this, we wrote out a strategy for that. We said when you have fractions inside of fractions, get a single fraction in your numerator, get a single fraction in your denominator, and then if you have a single fraction divided by a single fraction, you have a rule for a fraction divided by a fraction, you can multiply by the reciprocal. So currently, on the right-hand side, we have a single fraction in our denominator, but we do not have a single fraction in our numerator. So I'm going to multiply this. 1, how do we subtract fractions? Need a common denominator. And now I have a common denominator of sine theta. So the top will be cos theta minus sine theta. And on the bottom, so I have successfully got a single fraction in my numerator and a single fraction in my denominator. Now, how do you divide fractions? You multiply by the reciprocal, so we keep the top one the same. And multiply, flip the bottom one and multiply. Rules for simplification of fractions. Okay? You can only simplify a factor if it's identical on the top and the bottom. You can only simplify factors if you're multiplying. You can't simplify factors if you're adding. If things are added or subtracted, like this, will get grouped together to be a single factor. So once I've grouped that together, I would never be allowed to cancel out this sine theta and this sine theta. That would not be allowed because this sine theta is in this other factor, and it's not identical. So what I would have to do, though, is I could simplify this sine theta and this sine theta. They're identical, and we are multiplying. One factor on the top and a factor on the bottom are identical. Multiplying across the top, multiplying across the bottom. You group things together that are adding and subtracting. You would be allowed to factor and cancel out that sine theta. This would leave you with cos theta minus sine theta all over cos theta. We look at the other side. They are identical. And we're all done. Okay. So here's the proof changing things to sine theta and cos theta. It involved lots of fractions, but really important fraction rules. If you are able to do these fraction rules, if you're able to change to sine and cos and use your fraction rules to get a single fraction on both sides, you can be almost guaranteed 80% on every single proof on every single test. There's just a few subtle things that you might be missing, but most of it you will get. This is like the most important strategy. That being said, sometimes we can do these proofs quicker if we notice other things. For example, in this one. If I wanted to do this proof quicker, I might have noticed that, hey, there's a way that I could change things here so the entire proof is only using one trig function. Could you see that you could decide either to change tangent to cotangent or cotangent to tangent, and if I change tangent to cotangent, then the only trig function I have in this whole proof is cotangent. That might make things quicker than changing to sine and cos. Or if I change the cotangent to tangent, that might make things quicker than changing to sine and cos. In this one, I would probably choose to change the tangent to cotangent because this side on the right is already a single fraction. And then I would have no fractions inside of fractions. If I wanted a single fraction on the left, because I'm subtracting two fractions, I'd need a common denominator, which would mean cotangent here and cotangent here. That's the common denominator of cotangent. Top becomes cotangent theta minus 1, and look at this. And we're done. Way faster, right? Much shorter. So someone might say, this proof is more beautiful than the last proof because it's shorter. Okay? Do you get more marks for this one compared to the other one? No. They are both 100%. You can choose whichever method you want to get to the proof. Okay? But you have to choose something. So sometimes I see students, they change to sine and cos and they're going, this is getting really long. Maybe there was a better way. And then they look back at the question and go, I wonder what if I did this instead. Well, try it. See what it does. Sometimes someone proves one proof one way. And then they go and start it again and say, I'm going to do the same question again, but I'm going to try a different method to see if it's quicker. So there's not only one right way to do these questions. Sometimes there's multiple ways. What would happen in this one if I decided to multiply this side by cotangent theta over cotangent theta? Is that allowed? Yes, because the green is equal to 1. You're allowed to multiply by 1. Now what would happen is on the bottom, cotangent times 1 would be cotangent. And on the top, I could distribute. Cotangent theta times 1 is cotangent theta. And cotangent theta times tangent theta, since they're reciprocals of each other, will be 1. Here's another way to do this in one step. Okay? You have different options. You can be a little creative as long as you're using mathematical rules that you have from before. Your rules for fractions, your rules for multiplying, and so on. Okay, questions for practice on this one. Circle 3, 5, 6, and 7, part I only. You don't have to do the verify part, just the proof.